Hello everyone. Today we will study equations of lines and planes. First of all, let me review the equation of a line in R2. Equation of a line in R2 is y equal to mx plus b. Here m represents the slope, b represents the y-intercept. For example, how do we graph this line? Y equal to 2 over 3x plus 1. How do we graph the line? Y equal to 2 over 3x plus 1. Here, for this graph, the y-intercept is 1. Slope is 2/3, which means rise is 2, long is 3. Slope is rise over long. Rise is 2, long is 3. Rise is 2, 1, 2. Long is 3. 1, 2, 3. That's another point. Rise is 2, 1, 2. Long is 3. 1, 2, 3. That's another point. Rise is 2. Long is 3. 1, 2. 1, 2, 3. Then connect all these points, we can make a line. That's the equation of a line in R2. Next, let me introduce equation of line in R3. First of all, let me introduce what is a line in R3. First of all, let me introduce what is a line in R3. Let R0 be a point in R3. And let V be a vector. A line L is defined as L is the set of S, Y, Z. L is a set of points S, Y, Z in R3 such that S, Y, Z equal to the vector function R of T, which is the point R0 plus TV, where T can be any real number. Here in this equation, R0 is a point, but V is a vector. In order to add a point to a vector, when we're doing calculation, we must consider R0 as a vector. That's called position vector. And same thing, if we try to let S point SYZ equal to the vector function R of T, we must also consider SYZ as a vector. It's also called a position vector. So the point SYZ and the point R0, they are points. But when we're doing calculation, we must consider them as vectors, and they are called the position vectors. Next, let me show you how this line L looks like in R3. So R0 is a point on the line. Suppose R0 is here. Since we consider R0 as a position vector, so consider this point R0 as the head of the vector, and origin is the tail of the vector. This is the position vector R0. This is the position vector R0. V is a vector in R3. Suppose that's vector V. When t equal to 1, we have R0 plus V. The point is here. When t equal to 2, we have R0 plus 2V. The point is here. When t equal to 3, we have r0 plus 3v. The point is here. So we can see that here, as t increases, the line keeps moving to the right. Now, when t is 0, we have r0. The point is here. When t is negative 1, we have r0 minus v. The point is here. When t is negative 2, the point is here. When t is negative 3, the line keeps going to the left. So as t decreases, the line goes to the left. So here we can see that as t varies, we have a line here. This line is line L. Note here, the line L, this line L is called a line determined by the vector v passing through the point r0. This line L is called a line determined by the vector v passing through the point r0. And the vector v is called the directional vector of the line. Here, the vector v is called the directional vector of the line L. Also, here we consider the equation r of t equal to r0 plus tv as equation of the line. So the equation of the line is this equation, r of t equal to r0 plus tv. R0 is a point, but we consider it's a vector when doing calculation. It's called position vector. Next, let's do an example about equation of a line. Find the equation of the line. Passing through points -2, 1, 0 and 1, 3, 5. Find the equation of a line passing through points -2, 1, 0 and 1, 3, 5. In order to find equation of a line, we must know a point on the line and the directional vector of the line. If we know 2 points, here we have a point on the line. How do we find the directional vector? To find the directional vector, we can draw a vector between 2 points. Use head minus tail, we can find a vector. We can find the directional vector. So a point on the line, r0, I can pick any point. Could be either the first point or the second point. Here, let me use the first point. When we're doing calculation, we consider this point as a position vector. So we run the point as a vector, as a position vector. Now, how do we find the directional vector v? We can find a vector between these 2 points. So use head minus tail. Let's call this point head, this point tail. Head minus tail. 1 minus -2 is 3. 3 minus 1 is 2. 5 minus 0 is 5. Head minus tail, that's the position vector. That's the directional vector. Then use equation of line. R of t is r0 plus tv. Plug in. R0 is -2, 1, 0. V is 3, 2, 5. If we add them up, here we have -2, 1, 0. If I distribute t, I get 3t, 2t, 5t, which is -2 plus 3t, 1 plus 2t, and 0 plus 5t, which is 5t. This is r of t. This is equation of the line. This is the equation of the line. And this equation is called the vector equation. This equation is called the vector equation of the line. Here, in this vector, the first component represents x equal to -2 plus 2t. The second component is represent y equal to 1 plus 2t. The third component represents z equal to 5t. These equations together, they are called the parametric equation of a line. These equations together, they are called the parametric equation of the line. They are called the parametric equation of the line. Here, t can be any real number. Next, let's observe this function, this equation here. They all have a variable t. If we solve each equation for t, what do we get? They all have a variable t. If we solve each equation for t, what do we get? If I solve the first equation for t, I have t equal to x plus 2 over 3. If I solve the second equation for t, I have t equal to y minus 1 over 2. If I solve the third equation for t, I have t equal to z over 5. So these three expressions, they all equal to t. If I write them together, I have s plus 2 over 3 equal to y minus 1 over 2 equal to z over 5. That's another way to write equation of a line. And this is called the symmetric equation of a line. That's another way to write a line. And this is called the symmetric equation of a line. This is called a symmetric equation of a line. So for equation of a line, we have three ways to write equation of a line. We have three ways to write equation of a line. In general, if the problem doesn't specify which way they want, we must write the answer in a parametric equation, in the form of parametric equations. If the problem doesn't specify which form, we usually write the answer in the form of parametric equation. Next, let's look at a different example. Let L be a line x minus 1 over 3 equal to y plus 2 over 2 equal to z minus 3 over 5. Part A, find the intersection of the line in the xy plane. Part B, does the line intersect the z-axis? Here in this problem, the line L is given in the form of symmetric form. In general, we must rewrite the equation in parametric form first. In general, we must rewrite the equation in parametric form first. So here, I set each part equal to t, since they're all the same. Set each part equal to t. So we have s minus 1 over 3 equal to t. Y plus 2 over 2 equal to t. Z minus 3 over 5 equal to t. Set each of them equal to t, then solve an equation for t. So for the first equation, I can multiply both sides by 3. S minus 1 equal to 3t. For the second equation, I multiply both sides by 2. Y plus 2 equal to 2t. For the third equation, I multiply both sides by 5. z minus 5, z minus 3 equal to 5t. Then get s, y, z by itself. S equal to 1 plus 3t. Y equal to negative 2 plus 2t. Z equal to 3 plus 5t. That's the parametric form of the equation of the line. Next, let's solve the problem. First question. Find the intersection of the line in the xy plane. We know that for all points in the xy plane, the z component must be 0. For all points in the xy plane, the z component must be 0. So here we set the z component equal to 0. Solve for t. If I solve for t here, t is negative 3 over 5. Then plugging t, I can find the x and y components. Plugging t, I can find x and y coordinates. X equal to 1 plus 3 times negative 3 over 5. That's 1 minus 9 over 5, which is negative 4 over 5. Y equal to negative 2 minus 2 times negative 2 plus 2 times negative 3 over 5, which is negative 2 minus 6 over 5. That's negative 16 over 5. So the intersection in the xy plane is the point negative 4 over 5, comma, negative 16 over 5, comma, 0. Part B. Does the line intersect the z-axis? We know that for all points in the z-axis, both the x and y coordinates must be 0. For all points in the z-axis, both x and y component must be 0. For this line, if the xy component cannot be 0 at the same time, then this line doesn't intersect the z-axis. For this line here, if the x and y component cannot be 0 at the same time, then this line doesn't intersect the z-axis. So let's set both x and y component equal to 0. Set s equal to 1 plus 3t equal to 0. And y equal to negative 2 plus 2t equal to 0. Solve for t. If I solve for t here, t is negative 1/3. If I solve for t here, t equal to positive 1. So we can see that the x and y coordinate equal to 0 for different t values. That means x and y component cannot be 0 at the same time. If x and y component cannot be 0 at the same time on this line, if the x and y component cannot be 0 at the same time, this line doesn't intersect the z-axis. Since the x and the y coordinate cannot be 0 at the same time, the line L doesn't intersect the z-axis. Since the x and y coordinate cannot be 0 at the same time, this line L doesn't intersect the z-axis. Next example, let lines L1 and L2 be defined as L1 is the line x equal to 2 plus 4t, y equal to 3 plus t, z equal to 1 plus t. L2 is the line that s equal to 4 plus 2t, y equal to 5 plus 2t, z equal to 2 plus t. Determine whether L1 and L2 are parallel, skew, or intersecting. We know that in 2D, two lines is either parallel or intersecting. In 2D, two lines is either parallel or intersecting. In 3D, there are three cases. Two lines, they could be parallel. intersecting, or they could be skew. That means not parallel, not intersecting. So in 3D, there are three cases. Two lines could be parallel, intersecting, or skew, which means they are not parallel, not intersecting. So here, there are three cases. First of all, let's determine whether these two lines are parallel. To check if two lines are parallel, look at their directional vector. So for line 1, the directional vector is the component of t, the coefficient of t. Coefficient of t is 4, 1, negative 1. The coefficient of t is the directional vector of the line. For v2, the directional vector is also the coefficient of t, which is 2, 2, 1. The coefficient of t is the directional vector of the line. So let's check, does v1 and v2 parallel? Look at the ratio here. Look at the ratio between these two vectors. For 4 and 2, the ratio is 2. For 1 and 2, the ratio is a half. For 1 and negative 1, the ratio is negative 1. Since every component has different ratios, these two vectors, v1 and v2, they are not parallel. So v1 and v2, they are not parallel. Since v1 and v2 are not parallel, that means the line L1 and L2, they are not parallel. So they are not parallel. Next, if two lines are not parallel, there are two cases. Either they are intersecting or they are skew. If two lines intersect each other, that means they share a point. If two lines intersect each other, means they share a point. There's a point that x, y, z component, they are all the same. So we set x, y, z component equal to each other. For both lines, set x, y, z component equal to each other. So for an s component, if I set s component equal to each other, I have 2 plus 4t equal to 4 plus 2t. If I set a y component equal to each other, I have 3 plus t equal to 5 plus 2t. If I set a z component equal to each other, I have 1 minus t equal to 2 plus t. But the thing is, when two lines intersect, they may come to this point at different t values. For example, the first line may come to this point when t equal to, for example, equal to 0. The second line may come to this point, for example, when t equal to 3. So this point, they may intersect at this point for different t values. Therefore, in order to solve the equation, for the first line, I set a t value to be t1. For the second line, I set a t value to be t2. Since they may intersect at different t values, then solve this equation for t1 and t2. If there is solution for t1, t2, then two lines intersect. However, if there's no solution for t1, t2, then two lines skew. That means they don't intersect each other. If there's no solution for t1, t2, that means two lines skew. That means they don't intersect each other. So let's try to solve this equation for t1 and t2. If I simplify the first equation, it can be rewritten as 4t1 minus 2t2 equal to 2. If I simplify the second equation, it can be rewritten as t1 minus 2t2 equal to 2. If I simplify the third equation, it can be rewritten as negative t1 minus t2 equal to 1. We try to solve this equation for t1 and t2. Let's try to eliminate t1 first. If I add the second and third equation together, I get negative 3 t2 equal to 3. So I get t2 equal to negative 1. Next, I substitute t2 into all three equations and solve for t1. If all solutions for t1 are the same, that means this system of equation is consistent. So two lines intersect. Otherwise, if I plug in t2, I get different solutions for t1. That means this system of equation is inconsistent. So two lines skew. So let's plug in t2. In the first equation, if I plug in t2, I get negative 2 times negative 1 equal to 2. That means negative 4t1 plus 2 equal to 2. Negative 4t1 equal to 0, t1 equal to 0. If I substitute t2 into the second equation, I get t1 minus 2 times negative 1 equal to 2. t1 plus 2 equal to 2. So t1 is 0. In the third equation, if I plug in t2, I get negative t1 minus negative 1 equal to 1. Negative t1 plus 1 equal to 1. Negative t1 is 0, t1 is 0. So in all three equations, I get the same value for t1. That means the system of equation is consistent. These two lines, L1, L2, intersects when t1 equal to 0, t2 equal to negative 1. So two lines intersect. Now, if two lines intersect, there must be an intersection. If two lines intersect, there must be intersection. How do we find intersection? We know two lines intersect when t1 equal to 0, t2 equal to negative 1. So I plug in t1 into the first line, plugging t2 into the second line, I can find intersection. So in line 1, when t1 equal to 0, the s component is 2, y component is 3, z component is 1. In line 2, we should get the same point. If we calculate correctly, we should get the same point. In line 2, when t2 equal to negative 1, in line 2, when t2 equal to negative 1, we have s equal to 4 plus 2 times negative 1. Which is 2. Y equal to 5 plus 2 times negative 1. Which is 3. Z equal to 2 plus negative 1. Which is 1. So we get the same point. The intersection of line 1 and line 2 is the point 2, 3, and 1. So two lines intersect. The intersection is 2, 3, 1. They intersect at the point 2, 3, and 1. Next, I want to show you a different way to find equation of a line passing through 2 points. Let P and Q be 2 points in R3. The equation of the line passing through points P and Q can be written as R of t equal to 1 minus t times point P plus t times point Q for all t values. T can be any real number. In this equation, we must consider point P and point Q as position vectors because R is a vector function. In this equation, we must consider point P and point Q as vector functions, as position vectors. So, equation passing through 2 points P and Q. In this equation, when t is 0, if I plug in 0 for t, I get 1p plus 0q, which is p. When t is 0, we are here at point P. When t is 1, I get 0p plus 1q. We are here at point Q. So as t varies, we have a line here. That's another way to write equation of a line passing through 2 points. That's another way to write equation of a line passing through 2 points. Next, let's look at a simple example. Find the equation of a line passing through points -2, 1, 0 and 1, 3, 5. Find equation of a line passing through these 2 points. So here we can consider the first point as point P. Consider the second point as point Q. Then plug into this equation here. R of t equal to 1 minus t times point P. Here, when we plug in, we must write P and Q as a vector. Because R of t is a vector function. So when we plug in, we must write point P and Q as a vector, as a position vector. Then simplify. I can distribute 1 over t. I can distribute 1 minus t. I get -2 times 1 minus t, 1 minus t, 0, plus t, 3t, 5t. If I distribute -2, I get -2 plus 2t, 1 minus t, 0, plus t, 3t, 5t. Then add these 2 vectors together. I have -2 plus 3t, 1 minus 1 plus 2t, and 5t. If we run the answer in parametric equation form, in the form of parametric equation, I have x equal to -2 plus 3t, y equal to 1 plus 2t, z equal to 5t, where t can be any real number. In general, when we are looking for equation of line, if the problem doesn't specify how to write the answer, we write the answer in the form of parametric equations. Next, we will study equation of planes in R3. First of all, let me introduce what is a plane in R3. Let R0 be a point in R3. And let u and v be 2 vectors, be 2 non-parallel vectors in R3. Let u and v be 2 non-parallel vectors in R3. A plane M is defined as a plane M is defined as M equal to the set of points S, Y, Z in R3. Where S, Y, Z equal to the parametric equation R of S and T, that equal to R0 plus SU plus TV, where S and T can be any real number. Here in this equation, we must consider R0 and the point S, Y, Z as position vectors. Here we must consider the point S, Y, Z and the point R0 as position vectors. Because this is a vector function, and U and V are vectors. When we're adding point to vector, we must consider a point as a position vector. Next, let me show you the picture, how this plane M looks like. Let me show you a picture. So R0 is a point in R3. Suppose R0 is here. We consider R0 as a position vector. So we draw a vector whose head located at R0, tail located at origin. This is the position vector R0. This is the position vector R0. And U and V, they are two non-parallel vectors. Assume that's vector U, that's vector V. Now, when S is 1, T is 0. When S is 1, T is 0, we have R0 plus U, which is here. We have this point here. When S is 2, T is 0, we are here. When S is 2, T is 0, we have R plus 2U, we are here. When S is 3, T is 0, we are here. When S is -1, we go to the other side. When S is -1, T is 0. When S is -2, T is 0, we are here. Next, when S is 0, T is 1, we are here. When S is 0, T is 1, we are here. When S is 0, T is 1, we get R plus U. R0 plus U, we are here. When S is 1, T is 1. When S is 1, T is 1, we have R0 plus S, R0 plus U plus V. R0 plus U plus V, we are here. When S is 2, T is 1, we are here. When S is 2, T is 1, we have R0 plus 2U plus V. R0 plus 2U plus V, we are here. And so on. When S is 3, T is 1, we are here. And when S is -1, T is 1, we are here. When S is -1, when S is -2, T is 1, we are here. When S is 0, T is 2, we are here. When S is 0, T is 2, we got R0 plus 2V. R0 plus 2V, we are here. when s is 1, t is 2. When s is 1, t is 2, we got r0 plus u plus 2v. r0 plus u plus 2v, we are here. When s is 2, t is 2, we are here. 2u, r0 plus 2u plus 2v. 2u plus 2v, we are here. And similarly, when s is -1, t is 2, we are here. When s is -2, t is 2, we are here. So here we can see that all these points together form a plane. All these points together form a plane, and this is plane M. All these points together form a plane. This is plane M. If we plot all these points as s and t values, it forms a plane. This is plane M. The set of all these points form a plane, and this is plane M. Note, here, the plane M is called a plane. Determined by vectors u and v passing through R0. Here M is called plane determined by vectors u and v passing through the point R0. And this equation, R of st equal to R0 plus su plus tv, it's called equation of a plane. This equation, R of st equal to R0 plus su plus tv, is called equation of a plane. So the equation of a plane is written as R of st equal to R0 plus su plus tv, where R0 is a point in R3, and u and v are two non-parallel vectors. R0 is a point in R3, and u and v are two non-parallel vectors. In this equation, we must consider R0. When we plug in, we must consider R0 as a position vector. Since everything here is vector, we must consider R0 as a position vector. This is the equation of a plane. Next, let's look at an example. Let p equal to 2, -4, -3 be a point in R3, and let vector u equal to 4, -1, 2, and vector v equal to 2, -3, -2. Find the equation of the plane determined by vectors u and v passing through point P. So here we are looking for equation of a plane. Equation of a plane is R of s comma t equal to R0 plus su plus tv, where R0 is a point on the line, on a plane, and u and v are two non-parallel vectors. Let's plug in. R0 is a point here, P is a point on the plane. So plug in P for R0. When I plug in, I must write P as a vector, because I consider point P as a position vector. So P is 2, -4, -3 plus s times u. U is the vector 4, -1, 2. T times v. V is the vector 2, -3, -2. That's R of st. Then distribute s and t. I get 4s minus s, 2s. Distribute t, I get 2t, -3t, negative 2t. Then add these three vectors together. I get 2 plus 4s plus 2t. That's the first component. The second component is negative 4 minus s minus 3t. The third component is negative 3 plus 2s minus 2t. This is the equation of the line. This equation is called the vector equation of the line. This equation is called the vector equation of the line. If we write each component by itself, s equal to 2 plus 4s plus 2t, y equal to negative 4 minus s minus 3t, z equal to negative 3 plus 2s minus 2t, where s and t can be any real number. These three equations together is called parametric equations of equation of line. These three equations together, they are called parametric equations of a line. They are called parametric equations of a line. Next, let me introduce some terminologies about lines and planes. Let L1 and L2 be two lines. We say L1 and L2 are parallel if their directional vectors are parallel. Let L1 and L2 be two lines. We say L1 and L2 are parallel if their directional vectors are parallel. Next, let V be a vector and let L be a line. We say vector V is parallel to L, to line L, if vector V is parallel to the directional vector of line L. We say vector V is parallel to line L if V is parallel to the directional vector of line L. When vector V is parallel to line L, we can also say that vector V lies on line L. When vector V is parallel to line L, we can also say that vector V lies on line L. For example, suppose that's line L. This is vector V. Vector V is parallel to line L. That means vector V is parallel to the directional vector of line L. If I shift vector V here, if I shift vector V to line L, these two vectors, they are exactly the same vector. If I shift vector V here, These two vectors are exactly the same vector. So I can say vector v lies on line L. Next, let L1 and L2 be two lines. We say L1 is perpendicular to L2 if their directional vectors are perpendicular. Let L1 and L2 be two lines. We say L1 is perpendicular to L2 if their directional vectors are perpendicular. Next, let V be a vector and let L be a line. We say vector V is perpendicular to line L if vector V is perpendicular to the directional vector of line L. Let V be a vector and let L be a line. We say vector V is perpendicular to line L if vector V is perpendicular to the directional vector of line L. Next, let L be a line. And let M be a plane. We say line L is parallel to plane M if, here we have two cases, if L lies on plane M, if line L lies on plane M. That's plane M, that's line L. If line L lies on plane M, we can say L is parallel to plane M. Or they don't have any intersection. They have no intersections. They have no intersection means the distance between the line and the plane is the same everywhere. That's plane M. That's a line M. That's a line L. Such that the distance between the plane and the line is the same everywhere. The distance between the plane and the line is the same everywhere. So we say L is parallel to plane M if either L lies on plane M or they have no intersection. I'll show you how to verify this later. Next, let V be a vector and let M be a plane. We say V is parallel to plane M. We say vector V is parallel to plane M. if vector v lies on a line which is parallel to plane M. We say vector v is parallel to plane M if v, for example, if v lies on a line which is parallel to plane M. When vector v is parallel to plane M, we can also say that vector v lies on plane M. When vector v is parallel to plane M, we can also say that vector v lies on plane M. For example, if this vector v is parallel to plane M, I can shift this vector to plane M. This vector has exactly the same direction and the same magnitude. They are exactly the same vectors. So we can say vector v lies on plane M. These two vectors, they are exactly the same vector if I shift it here. So we can say vector v lies on plane M. Next, let v be a vector and let M be a plane. We say vector v is perpendicular to the plane. So vector v is perpendicular to plane M if vector v is perpendicular to every vectors that lies on plane M. Let v be a vector and let M be a plane. We say vector v is perpendicular to plane M if vector v is perpendicular to every vector that lies on plane M. Suppose that's plane M, that's vector v. If vector v is perpendicular to every vector that lies on plane M, if vector v is perpendicular to every vector that lies on plane M, then we say vector v is perpendicular to plane M. Next, let L be a line. And let M be a plane. We say line L is perpendicular to plane M if the directional vector of line L is perpendicular to plane M. We say line L is perpendicular to plane M if the directional vector of line L is perpendicular to plane M. For example, let's plane M. This is line L. If the directional vector of line L is perpendicular to plane M, then we say line L is perpendicular to plane M. Next, let's look at the theorem. Let M be a plane determined by vectors u and v, where u and v are not parallel, passing through a point P. Then, for all vectors w, if w lies on M, then w can be written as w equal to au plus bv, where a and b are real numbers. Here, this expression au plus bv, this is called a linear combination of u and v. This is called a linear combination of u and v. That means for all w, if w lies on M, then w can be written as a linear combination of u and v. So let's prove it. Since M is a plane determined by vectors u and v passing through P, then all points on M can be expressed as R of St equal to R0, here R0 is P, plus Su plus Tv, where S and T are real numbers. That's the equation of a plane. R0 plus Su plus Tv, here R0 is point P. That's a point on the plane. Let Q be an arbitrary point on the plane. Let Q be an arbitrary point on plane M. Then Q can be written as P plus AU plus BV for some real number A and B. If Q is a point on M, then Q can be written as P plus AU plus BV for some real number A and B. Next, if I subtract P from both sides, I have Q minus P equal to AU plus BV. Here, Q minus P represents a vector. Consider a vector head minus tail. Q minus P, consider that's a vector, head minus tail. So Q is the head, P is the tail. So Q minus P represents a vector from P to Q, which is vector PQ. Q minus P represents the vector from P to Q, which is vector PQ. Head minus tail. Q is the head, P is the tail. So vector PQ is AU plus BV. This statement is true for all point Q. This statement is true for all point Q. Since Q is an arbitrary point, this is true for all point Q on M. Since W, vector W lies on M, and point P is also lies in M, then if we shift the tail of W, to P, the head of W also lies on M. Since W lies on M, P also lies on M. If we shift the tail of W to P, then the head of W lies on M. So consider this is the plane M. P is a point on the plane. Suppose that's a vector W lies on plane M. If I shift the tail of W to P, since W lies on M, its head also lies on M. Since W lies on M, the head of W also lies on M. Let point Q be the head of W. Let point Q be the head of W. Since Q could be any point on M, let Q be the head of W. Then vector PQ will be the same as the vector W. If I let the head of W be Q, then vector PQ will be the same as W, PQ, head minus tail. Head minus tail, vector PQ is the same as vector W. Therefore, if I plug in W here, if I plug in W for vector PQ, I have W equal to AU plus BV for some real numbers A and B. For some real numbers A and B. So this theorem says if W lies on a plane determined by vector U and V, then we can always write W as a linear combination of U and V. If W lies on a plane depends on vectors U and V, then I can always write W as a linear combination of vectors U and V. Next, let M be a plane determined by vectors U and V passing through a point P, and let W be a vector which lies on plane M. Then, by the previous theorem, W can be written as a linear combination of vectors U and V, which means W equal to AU plus BV for some real numbers A and B. Here the question asks to find A and B. We know that since W lies on plane M, which is determined by vectors U and V, by the previous theorem, W can be written as a linear combination of U and V, which means W equal to AU plus BV for some real numbers A and B. How do we find A and B here? How do we find A and B? How do we find real numbers A and B that make W equal to AU plus BV? So let's do this. If I apply cross product multiply both sides by v. If I apply cross product, multiply both sides by v, then what do we get? Left side get w cross v. Right side get au plus bv cross v. Then apply distributive property. If I distribute v, I get w cross v equal to au cross v plus bv cross v. Since bv and v, they are parallel vectors, when we do cross product for two parallel vectors, the answer is 0. When we apply cross product to two parallel vectors, the answer is 0. So this answer can be rewritten as w cross v equal to a times u cross v plus 0. We can drop 0 here. Next, how can we get a by itself? There's no division for vector. This is a vector. We can't divide both sides by this vector. This is a vector. We can't divide both sides by this vector. What can we do here? Next, apply dot product. Apply dot product. Multiply both sides by this vector. Apply dot product. Multiply both sides by this vector u cross v. Apply dot product. Multiply both sides by u cross v. Then leave the left side the same. On the right side, u cross v dot u cross v is the magnitude of u cross v squared. According to the theorem that vector a dot a is always magnitude of a squared. That's the theorem. For any vector a dot a is always magnitude of a squared. So this is a vector. U cross v is a vector. A vector dot itself is the magnitude of the vector squared. Then the magnitude of a vector square is a constant. That's a number. I can divide both sides by this number. So a equal to w cross v dot u cross v over the magnitude of u cross v squared. Here I get a by itself. So a equal to vector of w cross v dot u cross v over magnitude of u cross v squared. Now, how do we find b? Very similarly, start over. How do we find b? I first of all apply cross product, multiply both sides by u. Apply cross product, multiply both sides by u. Then leave the left side the same. On the right side, distribute u. I get au cross u plus bv cross u. And here we can see that au and u, they are parallel vectors. The cross product of two parallel vectors is 0. Cross product of two parallel vectors is 0. So this is 0. I have w cross u equal to bv cross u. Next, we look at b by itself. Again, this is a vector. We cannot divide both sides by a vector. So next, I can multiply both sides by the same vector. Use dot product. Multiply both sides by u cross v. Use dot product. I get w cross u dot v cross u equal to b times v cross u dot itself v cross u. Then leave the left side the same. W cross u dot v cross u equal to b times, since we have the same vector dot itself, that's the magnitude of u cross v, v cross u, magnitude of v cross u square. Then this is a scalar. Magnitude square is a scalar. I can divide both sides by this scalar. So b equal to w cross u dot v cross u over magnitude of v cross u square. So b can be written as w cross u dot v cross u over magnitude of u cross v square. V cross u square and u cross v square, the magnitude is the same. They point to opposite direction, but the magnitude must be the same. For these two vectors, u cross v and v cross u, they point to an opposite direction, but their magnitude is the same. So I can write the bottom as u cross v. V cross u is the same as u cross v. That's how we find a and b. Once I can find a and b, I can write w in terms of au plus bv. Next, let me show you a different way to find equation of a plane. Let p equal to x0, y0, z0 be a point in R3. And let u and v be two non-parallel vectors. Suppose M is a plane determined by vectors u and v. Passing through point P. Then for all point Q in the plane M, for all point Q equal to SYZ in plane M, Q can be written as P plus SU plus TV. For some real numbers S and T, this equation comes from the equation of a plane. Let R of ST equal to R0 plus SU plus TV, where S and T are real numbers. This equation comes from the equation of a plane. Next, if I subtract P from both sides, then Q minus P equal to SU plus TV. Subtract P from both sides. Q minus P equal to SU minus TV. Then Q minus P represent a vector from P to Q. A vector can be represented by head minus tail. Here Q is the head, P is the tail. So q minus p represents a vector pq. That's the head, that's the tail. Head minus tail. Q is the head, p is the tail. Then vector pq equal to su plus tv. Next, I'll find a new vector n. The n equal to a, b, c. Be a vector with n perpendicular to u and n perpendicular to v. Since n is perpendicular to both u and v, this n can be found by using the cross product u cross v. Or n could be any vector that's perpendicular to the cross product of u and v. N could be any vector that's perpendicular to the cross product of u and v. So this vector n is a vector that's perpendicular to both u and v. Next, if I apply dot product, I multiply both sides by vector n. What do I get? If I apply dot product, multiply both sides by vector n, what do I get? In this equation, if I apply dot product, multiply both sides by vector n, what do I get? I can leave the left-hand side the same. On the right side, I distribute n. I get s u dot n plus t times v dot n. Since n is perpendicular to u, so the dot product of u and n is 0. And since n is also perpendicular to v, the dot product of v and n is also 0. So I get 0 plus 0. Since n is perpendicular to u, the dot product is 0. Since n is perpendicular to v, the dot product is 0. I get 0 over 0. I get 0 plus 0, which is 0. Which is 0. And what's vector PQ? Vector PQ, we can use head minus tail. Take point Q minus point P. So vector PQ can be written as x minus x0, comma, it's a vector. X minus x0, comma, y minus y0, comma, z minus z0. For vector PQ, I use head minus tail. Head minus tail, q minus p, x minus x0, y minus y0, z minus z0. That's vector pq. Vector n is the vector a, b, c equal to 0. If we apply dot product, I take the first component times first component, second component times second component, the third component times the third component. So x minus 0 times a is a times x minus 0. Y minus y0 times b is b times y minus y0. Z minus z0 times c is c times z minus z0 equal to 0. That's also an equation of a plane. And this equation has a name. That's called the normal form of a plane. It's called a normal form of an equation of a plane. This is called the normal form of an equation of a plane. If I simplify this equation, I can distribute A. I can distribute A into the parentheses and B into the parentheses, C into the parentheses. What do I get? I get AX minus AX0 plus BY minus BY0 plus CG minus CG0 equal to 0. If I keep AX, BY, CG on the left side and bring the rest over, I have ax plus by plus cg equal to ax0 plus by0 plus cg0. Since point P is a fixed point, so x0, y0, z0, they are constants. And ABC is also constant. Constant plus constant times constant plus constant, this is a constant. So I can write ax plus by plus cg equal to d by letting d equal to ax0 plus by0 plus cg0. That's a new form of equation of plane. This is also equation of a plane. This is also equation of a plane. This is called the standard form of a plane. This is called a standard form of equation of a plane. This is called the standard form of equation of a plane. And in this equation here, this vector n is called the normal vector of the plane. This vector n is called the normal vector of the plane. And the component of vector n is the coefficient of s, y, z. In the standard form, the component of vector n is the coefficient of s, y, z. The component of the normal vector are the coefficients of x, y, and z. Keep this note in mind. This new vector n is called the normal vector of the plane. And the component of the normal vector is always the coefficient of s, y, z. This form is called the normal form of the equation of a plane. And this form is called the standard form of the equation of a plane. Next, let's look at the theorem. Let M be a plane determined by vectors u and v passing through a point P, and let vector M be the normal vector of plane M. If vector W lies on plane M, then the normal vector n is always perpendicular to vector W. Let's prove it. Since M is a plane determined by vectors u and v, and vector W lies on plane M, then by the previous theorem, W can be written as a linear combination of u and v. That means W equal to AU plus BV for some real numbers A and B. If W lies on plane M, then W can be written as a linear combination of u and v. Then that means W equal to AU plus BV for some AB, for some real number A and B. Next. Since n is the normal vector of plane M, then N is parallel to the cross product of U and V. Since N is a normal vector of plane M, then N is parallel to the normal vector of N is parallel to the cross product of U and V. So vector N is perpendicular to vector U, and vector N is perpendicular to vector V. Hence, their dot product must be 0. N dot U must be 0. And N dot V must be 0. Now for this problem, we try to show that the normal vector N is perpendicular to the vector W. In order to show two vectors are perpendicular, we can try to show that their dot product is 0. So let's take N dot W. N dot W can be rewritten as N dot AU plus BV, because vector W is AU plus BV. Then I can distribute N. I get N dot AU plus N dot BV. Then by a property of dot product, I can pull out the constant. I can pull the coefficient outside, right? A times N dot U plus B times N dot V. And we know that since vector N and U, they are perpendicular, the dot product is 0. And since the dot product of NV is also 0. So you get A times 0 plus B times 0, which is 0. Since the dot product of N and W is 0, then we can say that they are perpendicular. So vector N is perpendicular to vector W. According to this theorem, we know that the normal vector of a plane is always perpendicular to all vectors that lie on the plane. So we can say that the normal vector of a plane is always perpendicular to the entire plane. So keep this note in mind. The normal vector of a plane is always perpendicular to the entire plane. Next, let's look at an example here. Find the equation of a line determined by vectors 3, 2, 4 and -2, 6, and 1, passing through a point 4, -1, -2. Here we are looking for equation of a plane. So far we have 4 different ways to write equation of a plane. Let me show you each way individually. First way, we can use vector function. We can use vector equations. Vector equation says R of ST equal to R0 plus SU plus TV, where R0 is a point on the plane. Here is 4, -1, -2. U and V are two vectors. Here we can take the first vector as U, second vector as V. So let's plug in R0. When we plug in R0, we need to write it as a point. Consider this point as a position vector. So 4, -1, -2, write it as a vector. S times V. V is the vector 3, 2, 4. Plus T times the vector -1, 6, and 1. -2, 6, and 1. Then simplify. We distribute S and T. 4, -1, -2 plus 3S, 2S, 4S. Distribute T, I get -2T, 6T, and 1T. Then add this vector together. I get 4, plus 3s minus 2t. In the middle, we have negative 1 plus 2s plus 6t. And the last component is negative 2 plus 4s plus t. This is RST. This equation is called a vector equation of a plane. That's the first way to write equation of a plane. That's called a vector equation of a plane. Next, if we write each component by itself, then we have x equal to 4 plus 3s minus 2t, y equal to negative 1 plus 2s plus 6t, z equal to negative 2 plus 4s plus t, where s and t can be any real numbers. These three equations together, they are called parametric equations of a plane. They are called parametric equations of a plane. Next, let me show you how to find equation of plane using normal vectors, using a normal vector. Normal vector n is the vector that parallel to the cross product of u and v. Normal vector n is a vector that parallel to the cross product of u and v. So let's compute u and v, the cross product of u and v first. For the cross product of u and v, I write ijk, write vectors ijk in the first row. That's the standard base in R3. Then write vector u in the second row. Write vector v in the third row. Negative 2, 6, and 1. Next, take determinant for this matrix. If I take determinant, I use cofactor expansion. I times determinant of the matrix 2, 4, 6, 1 minus j times the determinant of the matrix 3, 4, negative 2, 1 plus vector k times determinant of the matrix 3, 2, negative 2, 6. Then compute determinant for each matrix. For the first matrix, I get 2 minus 24, that's negative 22. J times 3 minus negative 8 is 11. Plus k times 18 minus negative 4, that's 22, positive 22. Write this as a vector. Write in vector form, I have negative 22, comma, negative 11, comma, 22. Normal vector is a vector that parallel to the cross product of u and v. So here, to make it a little simpler, I can pull out negative 11. If I pull out negative 11, I have 2, comma, 1, comma, negative 2. I can take this as my normal vector. I can take 2, 1, negative 2. I can take this as my normal vector. So here, my normal vector is 2, 1, negative 2. Next, I use the normal form of an equation of a line. The normal form of an equation of a line says a times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0. A times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0. Here, a, b, c, they are the components of the normal vector n. A, B, C are the components of the normal vector. x0, y0, z0 represent a point on the plane. x0, y0, z0 represent a point on the plane, which is 4, -1, -2. So let's plug in the numbers. A, B, C are the components of the normal vector. So I have 2, 1, -2. That's A, B, and C. X, Y, Z. X0 is 4, so I got -4 here. Y0 is -1, so I got -1, which is +1. Z0 is -2, so we get -2, which is +2. This is the normal form. This is a normal form of an equation of a plane. This is a normal form of an equation of a plane. This is a normal form of an equation of a plane. Next, if I distribute 2 and simplify this equation, what do I get? Distribute 2, 1, -2 and simplify the equation. I have 2x minus 8 plus y plus 1 minus 2z minus 4 equal to 0. If I write 2x, y, and 2z together, then combine the like terms, I have -a plus 1, that's -7. -7 minus 4 is -11. If I bring it over, it becomes +11. This is called the standard form of an equation of a plane. This is called the standard form of an equation of a plane. This is called the standard form of an equation of a plane. So we have 4 different ways to write equation of a plane. We have 4 different ways to write equation of a plane. We can write it as a vector equation, parametric equations, normal form of an equation, and a standard form of an equation. So there are 4 different ways to write equation of a plane. In general, if the problem doesn't specify which way to write the answer, we must write the answer in the standard form. In general, if the problem doesn't specify which form to write the answer, we must put the answer in standard form. For all your future problems, if the problem doesn't specify how to write the answer, we must always write the answer in the standard form. Next example, let 2x plus 3y minus 4z equal to 20 be the equation of plane M. The equations of line 1, line 2, and line 3 be defined as line 1, s equal to 2 minus 2t, y equal to 1 plus 3t, and z equal to -4 plus t. Line 2, s equal to 1 plus t, y equal to 2 minus 2t, and z equal to -3 minus t. Line 3, s equal to 2 plus t, y equal to -2t, and z equal to 1 minus t. Part A. Find the intersection of line 1 and plane M if possible. Sometimes for a plane and a line, if they are parallel, there are no intersections. If a line and a plane are parallel, there are no intersections. Part B. Find the intersection of line 2 and plane M if possible. Part C. Find the intersection of line 3 and M if possible. Let's look at part A first. Part A, we are looking for the intersection of line 1 and plane M. Plane M is 2x plus 3y minus 4z equal to 20. If I plug line 1 into plane M, I have 2 times 2 minus 2t plus 3 times 1 plus 3t minus 4 times -4 plus t equal to 20. This equation has only one variable, t. I can solve this equation for t. I have Distribute 2, I have 4 minus 4t. Distribute 3, I get 3 plus 9t. Distribute negative 4, I get positive 16 minus 4t equal to 20. Combine like terms, I have 23 plus t equal to 20. If I solve an equation for t equal to negative 3, that means when t equal to negative 3, line 1 intersects plane M. When t equal to negative 3, line 1 intersects plane M. In order to find intersection, I plug in t into line 1. In order to find intersection, I plug in t into line 1. So when t is negative 3, x equal to 2 minus 2 times negative 3, which is 2 plus 6 equal to a. Y equal to 1 plus 3 times negative 3. 3 times negative 3 is negative 9. 1 minus 9 is negative 8. Z is negative 4 plus t, and t is negative 3. Negative 4 plus negative 3 is negative 7. So the intersection between line 1 and plane M is the point a, negative 7. Part B. Find the intersection of line 2 and plane M if possible. Let's write down plane M first. Plane M is 2x plus 3y minus 4z equal to 20. So same procedure. I plug line 2 into plane M. If I plug in, I have 2 times 1 plus t plus 3 times 2 minus 2t minus 4 times negative 3 minus t equal to 20. Then solve this equation for t. I can distribute 2 first. If I distribute 2, I get 2 plus 2t. If I distribute 3, I get 6 minus 6t. If I distribute 4, I get 12 plus 4t equal to 20. Then combine like terms. 2t minus 4t is negative 4t. Negative 4t plus 4t, they get cancel. And for the constants, 2 plus 6 is 8. 8 plus 12 is 20. I get 20 over 20. This statement is true for all t values. That means the entire line 2 lies on plane M. So line 2 lies on plane M. If line 2 lies on plane M, the intersection between line 2 and plane M is line 2. It's the entire line 2. If a line lies on a plane, the intersection between the line and the plane is this entire line. Part C. Find the intersection of line 3 and plane M, if possible. Let me write down the equation of the plane first. 2x plus 3y minus 4z equal to 20. So in line 3, we plug in SYZ. Plugging SYZ from line 3, I have 2 times 2 plus t plus 3 times negative 2t minus 4 times z is 1 minus t, equal to 20. Solve this equation for t. I have 4 plus 2t minus 6t minus 4 plus 4t equal to 20. Then combine like terms. 2t minus 6t is negative 4t. Negative 4t plus 4t can cancel. Then for the constant, 4 minus 4 is 0. So I get 0 equal to 20. This is always false. 0 equal to 20 is false for all t values, which means line 3 doesn't satisfy the equation of a plane. So line 3 doesn't intersect plane M. Line 3 does not intersect plane M. So there are no intersection. If line 3 doesn't intersect plane M, that means actually this line 3 is parallel to plane M. If line 3 doesn't intersect plane M, that means line 3 actually parallel to plane M. Hence, there are no intersection between line 3 and plane M. Since there are no intersection between line 3 and plane M, we can say that in this example, line 3 is parallel to plane M. And line 3 doesn't lie on plane M. In the previous part, line 2 lies on plane M. We can also say that in this example, line 2, we can also say that line 2 is parallel to plane M. And line 2 lies on plane M. Let's look this problem over. When we plug in the equation of a line into the equation of a plane and solve for t, if we get only one solution for t, that means the line and the plane intersect at only one point. If a line and a plane intersect at only one point, that means they are not parallel to each other. If a line and a plane intersect at only one point, that means they are not parallel to each other. So in this example, we get only one solution for t. That means line 1 and plane M intersect at only one point. If they intersect at only one point, that means they are not parallel. So line 1 and plane M, they are not parallel to each other. In part B and part C, when we plug in the equation of a line into the equation of a plane and solve for t, we see that in both cases, t get completely cancelled. And if t get completely cancelled, we can tell that the line is parallel to the plane. When t get completely cancelled, we can tell that the line is parallel to the plane. And if we obtain a true statement here, when t get cancelled, if we obtain a true statement, that means the line lies on the plane. But if we obtain a false statement when t get completely cancelled, if we obtain a false statement, that means the line doesn't lie on the plane. Next, let's make note from the previous example. When we substitute the parametric equation of a line called R of t. When we substitute the parametric equation of a line R of t into the equation of a plane. And solve the equation for t. Case 1. If there's only one solution for t, then that means the line and the plane are not parallel. As in example 1, if there's only one solution for t, the line and the plane are not parallel. However, when we solve for t, if the variable t get cancelled completely, if the variable t gets cancelled completely, then the line and the plane are parallel. As in example part B and part C, if t get completely cancelled, that means the line and the plane are parallel. When t get completely cancelled, if a true statement is obtained, then the line lies on the plane. As in our example part B here, when t get cancelled, if a true statement is obtained, that means the line lies on the plane. The second part. When t gets cancelled completely, if a false statement is obtained, then the line doesn't lie on the plane. As our example part C here, when t get cancelled, if we're playing a false statement here, that means the line doesn't lie on the plane. So if the variable t get completely cancelled, then the plane and the line are parallel. If a true statement is obtained, the line is parallel to the plane and it also lie on the plane. If a false statement is obtained, then the line is parallel to the plane but it doesn't lie on the plane. Next example, let vector n equal to abc be the normal vector of plane M, and let vector w equal to def, and vector w is perpendicular to vector n. Show that vector w lies on plane M. In order to show a vector lies on a plane, we must show that the vector is parallel to the plane. In order to show a vector is parallel to a plane, we must show that the vector lies on a line that's parallel to the plane. So here, if we want to show that W lies on plane M, we must show that W lies on a line that's parallel to plane M. Let's prove it here. First of all, we try to find a line L which contains vector W. So let R0 be a point. Let R0 equal to x0, y0, z0 be a point in R3. Let L be the line determined by vector W passing through R0. Then, since line L is determined by vector W, then vector W lies on line L. If line L is determined by vector W passing through a point R0, then vector W lies on line L. Next, let's try to find the equation of line L. Equation of line L can be written as R of t equal to R0 plus t times directional vector here is W, t times W. R0, when we plug in, write it as a vector, x0, y0, z0 plus t times W. W is the vector def. Then distribute t, I get x0, y0, z0 plus dt, et, ft. Together it's x0 plus dt, y0 plus et, z0 plus ft. So the parametric equation for line is s equal to x0 plus dt, y equal to y0 plus et, and z equal to z0 plus ft. Next, we try to find the equation of plane M. For plane M, all we know is its normal vector. So we try to use normal vector to find equation of plane M. Let point Q equal to x1, y1, z1 be a point in plane M. Since we know it's normal vector, then the equation of plane M can be written as a times x minus s1 plus b times y minus y1 plus c times z minus z1 equal to 0. Here, in this equation, a, b, c represent the components of the normal vector. s1, y1, z1 is the component of a point on the plane. Next, we try to show that line L parallel to plane M. By the previous example, in order to show a line is parallel to a plane, we try to substitute the parametric equation into the equation of a plane. If the variable t get cancelled completely, then the line and the plane are parallel by the previous example. So here we try to substitute the parametric equation of the line into the equation of the plane. Substitute x, y, and z. If I substitute s, y, z, what do we get? We have a times x0 plus dt minus s1. b times y0 plus et minus y1 plus c times z0 plus ft minus z1 equal to 0. Let's simplify here. If I distribute a, I get ax0 minus ax1 plus a dt minus ax1. If I distribute b, I get by0 plus bet minus by1. If I distribute c, I get cz0 plus cft minus cz1 equal to 0. Then in this equation, I can write a term that contains t together. Our goal is try to cancel t out. So write a term that contains t together. So put a constant together, I have ax0 minus ax1 plus by0 minus by1 plus cz0 minus cz1, and put a term that contains t together. I have ad plus be plus cf times t equal to 0. Next, we know that vector w and vector n, they are perpendicular. If they are perpendicular, what can we say about that? If they are perpendicular, since vector w and vector n, they are perpendicular, then that means their dot product must be 0. When I apply dot product to w and n, I must get 0. So if I apply dot product, I have AD plus BE plus CF must be 0. The dot product of WM must be 0. So since the dot product is 0, this part must be 0. So this equation can be written as ax0 minus ax1 plus by0 minus by1 plus cz0 minus cz1 plus 0t equal to 0. So here, t get cancelled completely. There's no t left here. In this equation here. For this equation, t get cancelled completely. There's no t left. What's left here is ax0 minus ax1 plus by0 minus by1 plus cz0 minus cz1 equal to 0. By the previous problem, we know that if t get cancelled completely, the line and the plane are parallel. So, by the previous problem, line L is parallel to plane M. since in this equation here, t get cancelled completely. If this part is 0, then this is a true statement. That means line L lies on plane M, hence they are parallel. If this part is not 0, then this is a false statement. That means there's no intersection between line L and plane M. If there's no intersection between a line and a plane, that means they must be parallel. So in both cases, line L is parallel to plane M. Since vector W lies on line L and line L is parallel to plane M, then vector W is parallel to plane M. Hence we can say that vector W lies on plane M. That completes the proof for this problem. So this problem says, if n is the normal vector of a plane M and W is perpendicular to n, then W lies on plane M, which means if W is perpendicular to the normal vector of a plane, then W lies on the plane. So for all vector, if it's perpendicular to the normal vector of the plane, then this vector lies on the plane. Let's make note for this problem. Note: if a vector is perpendicular to the normal vector of a plane, then this vector lies on the plane. If a vector is perpendicular to the normal vector of a plane, then this vector lies on the plane. If I show you a picture here, it will make more sense to you. Assume this is plane M. N is the normal vector of the plane. Vector N is the normal vector of a plane. A normal vector is a vector that perpendicular to the entire plane. Let W be a vector that's perpendicular to a normal vector. So here, W is a vector that's perpendicular to the normal vector. Then here we can see that W parallel to plane M. This vector W parallel to plane M. If I shift W down to the plane, if I shift vector W down to the plane, we can see that this vector and this vector are exactly the same vector, and this vector lies on the plane. So we can say that if a vector is perpendicular to the normal vector of a plane, then this vector lies on the plane. Next example, let M be a plane determined by vectors U equal to 1, 2, 3, V equal to 2, 2, 2, passing through point P. Point P is 2, -4, -1. Part A, find the equation of plane M. Part B, let vector W be 1, 4, 7. Show that vector W lies on plane M. Part C, write vector W as a linear combination of vectors U and V. So W equal to AU plus BV for some real numbers A and B. Let's do part A first. Find the equation of plane M. So for part A, in order to find the equation of plane M, let's find the normal vector first. We know that normal vector of a plane is always parallel to the cross product of U cross V, where plane M determined by vectors U and V. So it's normal vector always parallel to u cross v. Let's compute the cross product here. Write vector I, j, k in the first row. That's the standard base of R3. Write vector u in the second row. And write vector v in the third row. Then use cofactor expansion to compute the determinant. Take I times determinant of the matrix 2, 3, 2, 2 minus j times the determinant of the matrix 1, 3, 2, 2 plus k times the determinant of the matrix 1, 2, 2, 2. Then compute each determinant individually. For the first matrix, the determinant here is 4 minus 6 is negative 2. For the second matrix, the determinant is 2 minus 6, which is negative 4. For the third matrix, the determinant is 2 minus 4, which is negative 2. Then write it in vector form. The component is negative 2, 4, negative 2. To make it easier, I can pull out negative 2. If I pull out negative 2, the vector is 1, negative 2, 1. I can take this as my normal vector. This normal vector parallels the cross product of u cross v. I can take my normal vector to be 1, negative 2, and 1. Next, I can use the normal form to write equation of a plane. Normal form is a times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0, where a, b, c is the component of the normal vector n, and x0, y0, z0 represent a point on the plane. For a point on the plane, I can use point P here. That's 2, negative 4, negative 1. So let's plug in. The normal vector is 1, negative 2, and 1. The point on the plane is 2, negative 4, negative 1. So you get x minus 2, y plus 4, z plus 1 equal to 0. Then simplify. If I distribute 1, I get x minus 2. If I distribute negative 2, I get negative 2y minus a. If I distribute 1, I get z plus 1. Then combine like term, put the answer in standard form. We have x minus 2y plus z. If I combine like term here, negative 2 plus negative a is negative 10. Negative 10 plus 1 is negative 9. And when I bring over, it becomes positive 9. That's the equation of a plane in a standard form. That's the equation of plane M in a standard form. Part B. Let W be a vector of 1, 4, 7. Show that vector W lies on plane M. According to the previous problem, we know that if a vector is perpendicular to the normal vector of a plane, then this vector, it lies on the plane. If a vector is perpendicular to the normal vector of the plane, then this vector lies on the plane. So here, if we try to show vector W lies on plane M, we try to show that vector W is perpendicular to the normal vector of plane M. Let's find the normal vector of plane M first. The normal vector of plane M is vector n. The normal vector can be read from the equation of a plane. The component of normal vector is the coefficient of s, y, z. In the equation of plane, the normal vector of the plane is the coefficient of s, y, z. Here we can read it from here. 1, negative 2, 1. That's the normal vector of plane M. The coefficient of s, y, z is the component of the normal vector. Next, we try to show that vector W and vector N, they are perpendicular. In order to show two vectors perpendicular, we try to show that their dot product is 0. So let's take the dot product. Since the dot product of Wn equal to 1 times 1 is 1, 4 times -2 is -8, 7 times 1 is 7, that's 0. Since the dot product is 0, we can say that vector W is perpendicular to vector N. Since W is perpendicular to the normal vector of plane M, then I can say that W lies on plane M. Since vector W is perpendicular to the normal vector of plane M, W lies on plane M. Part C. Write W as AU plus BV for some real numbers A and B. According to a problem we did earlier today, we know that if M is a plane determined by vectors U and V, and W lies on a plane, then W can be written as a linear combination of vectors U and V. So W equal to AU plus BV for some real numbers A and B. And A and B can be found using these two formulas. So let's use this formula to find A and B. According to the formula, A equal to the cross product of W cross V dot U cross V over the magnitude of U cross V square. B equal to the cross product of W cross U dot the cross product of V cross U over U cross V, magnitude of U cross V square. Let's first of all compute each cross product first. Let's compute W cross V first. For W cross V, write ijk, the standard base, on the first row. Write vector W in the second row. Vector W is 1, 4, 7. Put it in the second row. Write vector V in the third row. Vector V is 2, 2, 2. Then compute determinant. I get I times determinant of 4, 7, 2, 2 minus J times determinant of 1, 7, 2, 2 plus K times determinant of 1, 4, 2, 2. Then compute each determinant individually. 4 times 2 is A. 2 times 7 is 14. A minus 14 is -6. 1 times 2 is 2. 2 times 7 is 14. 2 minus 14 is -12. 1 times 2 is 2. 2 times 4 is 8. 2 minus 8 is -6. Then when I answer in vector form, I have -6, comma, +12, comma, -6. That's a cross product W cross V. Next, we compute the cross product W cross U. First of all, put ijk in the first row. Write vector W in the second row, which is 1, 4, 7. Write vector V in the third row. Vector U in the third row. U is a vector 1, 2, 3. Write vector U in the third row. Then compute the determinant. Use cofactor expansion. I times the matrix, determinant of the matrix 4, 7, 2, 3 minus J times determinant of the matrix 1, 7, 1, 3 plus k times determinant of the matrix 1, 4, 1, 2. Then compute each determinant individually. I times 12 minus 14, that's negative 2, minus j times 3 minus 7, that's negative 4, plus k times 2 minus 4, that's negative 2. Put it in vector form, that's negative 2 comma 4 comma negative 2. That's a cross product W cross U. Next, we compute the cross product U cross V. Next, we compute the cross product U cross V. According to part A, we know that the cross product U cross V is the vector negative 2, 4, negative 2. And V cross U is negative U cross V. V cross U is negative U cross V. So if I multiply this vector by negative 1, I get 2, negative 4, 2. Next, I copy everything over from the previous page. Let's continue. Here, next we'll compute the dot product W cross V dot U cross V. Dot product W cross V dot U cross V. That's 12 plus 48 plus 12, which is 72. And for B, I compute the dot product W cross U dot V cross U, which is negative 4 minus 16 minus 4, which is negative 24. Next, we compute the denominator, the magnitude of U cross V. Magnitude of the vector U cross V. This is vector U cross V. Let's compute the magnitude. It's square root of negative 2 square plus 4 square plus negative 2 square, which is 4 plus 16 plus 4. That's square root of 24. Then when we square this, we have square root of 24 square, that's 24. So that's the denominator. Here, A equal to the dot product of W cross V dot U cross V, which is 72, over the magnitude of U cross V square, which is 24. So A equal to 3. For B, the numerator is the dot product of W cross U dot V cross U, which is negative 24. The denominator is the magnitude of U cross V square, which is also 24. Negative 24 divided by 24 is negative 1. So here we found A is 3, B is negative 1. Let's check the answer. We want to verify that W equal to AU plus BV. So let's verify. AU plus BV equal to A is 3. Vector U is 1, 2, 3. U is the vector 1, 2, 3. B is negative 1. Vector V is the vector 2, 2, 2. If I distribute 3, we get 6. We get 3 comma 6 comma 9. If I distribute negative 1, I get negative 2, negative 2, negative 2. Then add these two vectors. 3 minus 2 is 1. 6 minus negative 2 is 4. 9 plus negative 2 is 7. That's the same as vector W. That's the same as vector W. So if we try to write W as a linear combination of U and V, we can use these two formulas to find coefficients A and B. But let me say this. In general, in real life, we don't use these two formulas to find the coefficients A and B. They are too much work. You see that in both formulas, we must compute 3 cross products. They are too much work. For those you know linear algebra, probably you know that there's a much easier way to find A and B. So for those you know linear algebra, let me show you a much easier way. You'll see that. In linear algebra class, we first of all put vector U in the first column. Vector U is 1, 2, 3. Put vector V in the second column. Vector V is 2, 2, 2. Put vector W in the third column. Vector W is 1, 4, 7. Then reduce the matrices. Reduce the matrices. If I multiply first row by negative 2, add it to the second row, I get 1, leave first row the same. I get 0, negative 2, and 2 in the second row. If I multiply first row by negative 3, add it to the third row, I get 0, negative 4, and 4 in the third row. Next, I can divide the second row by negative 2. If I divide second row by negative 2, I leave the first row and the third row the same. Next, I multiply first row by negative 2. Multiply second row by negative 2. Add it to the first row. I get 1, 0, 3. Leave the second row the same. I can multiply the second row by 4. Add it to the third row. I get 0, 0, 0. These numbers are A and B. So if you know linear algebra, you can get an answer in a much quicker way by reducing the matrix. However, if you don't know linear algebra, you must use a long way here to find A and B. There are no shortcuts. Next, let's look at a theorem. Let M be a plane determined by vectors U and V passing through a point P. Let N be the normal vector of plane M. If vectors W1, W2 lie on plane M, then M is parallel to the cross product of W1 and W2. Let's prove it. Here we know that M is a plane determined by vectors U and V, and W1, W2 are two vectors lie on plane M. By a theorem we learned earlier today, we know that if M is a plane determined by vectors U and V, and W lie on plane M, then W can be written as a linear combination of vectors U and V. So here, since plane M is determined by vector U and V, and vectors W1, W2, they both lie on plane M, then W1, W2 can be written as a linear combination of vectors U and V. Then W1 can be written as A1 times U plus B1 times V. W2 can be written as A2 times U plus B2 times V, where A1, A2, B1, B2 are real numbers. Since n is the normal vector of plane M, then vector n is parallel to the cross product of vector uv. Since plane M is determined by vectors u and v, and n is a normal vector of plane M, then n is parallel to the cross product of u and v. Next, let's compute the cross product. W1 cross W2. W1 is A1u plus B1v, and W2 is A2u plus B2v. Let's apply distribute property. FOIL this out. We have A1u cross A2u plus A1u cross B2v plus B1v cross A2u plus B1v cross B2v. We know that the vector A1u and A2u, they are parallel vectors. Cross product of any parallel vector is 0. So this is a 0 vector. Similarly here, the vector B1v and B2v, they are parallel vectors. Cross product of parallel vector is 0. Then what's left is these two terms. For these two terms here, I can pull out the constants. So for the first term, I can pull out A1, B2. If I pull out A1, B2, what's left is U cross V. For the second term, I can pull out B1, A2. If I pull out B1, A2, what's left is cross product V cross U. Then for V cross U here, if I switch the order, the sign will change from positive to negative. So this cross product can be rewritten as A1, B2, U cross V minus B1, A2, U cross V. Here, when I switch order for cross product, when I switch order, the sign changes from positive to negative. Next, you can see that these two vectors, they are exactly the same. So I can write the constant together. A1, B2 minus B1, A2 times U cross V. So here we have W1 cross W2 equal to A1, B2 minus B1, A2 times the cross product U cross V. This is a constant. A1, B2 minus B1, A2 is a constant. Since the cross product of W1 cross W2, this vector is a constant multiple of the other vector, that means they are parallel vectors. Since one of the vector is a constant multiple of the other vector, they are parallel vectors. Hence, W1 cross W2, this vector parallel to the vector U cross V. Since the normal vector n parallel to U cross V, and the vector U cross V parallel to the vector W1 cross W2, then by transitive property, we know that we can say that vector n parallel to the cross product W1 cross W2. By transitive property, n is parallel to U cross V. U cross V is parallel to W1 cross W2. So by transitive property, vector n is parallel to vector w1 cross w2. That completes the proof. Next, let's look over this theorem. This theorem says, for any vectors w1, w2 lie on plane M, the cross product of w1, w2 is always parallel to the normal vector of the plane. Therefore, the cross product of w1, w2 is always perpendicular to the entire plane. So let's make notes for this theorem. Note: for any two vectors lie on the same plane, their cross product is always parallel to the normal vector of the plane. And perpendicular to the entire plane. For any two vectors lie on the same plane, their cross product is always parallel to the normal vector of the plane and perpendicular to the entire plane. Let me show you a picture, it will make more sense to you. Suppose that's a plane M. There are two vectors lie on the plane, lie on the same plane. There are two vectors lie on the same plane. If I find a cross product, it generates a vector here. This vector is perpendicular to both vectors on the plane here. And we can see that this vector here is perpendicular to the entire plane. Next, let's look at an example. Let u equal to -1, -3, 4, and v equal to 2, -2, 1 be two vectors lie on a plane. And let p equal to 1, -3, -2 be a point on a plane. Find the equation of the plane. In order to find the equation of a plane, we must find the normal vector of the plane first. Here we know that u and v are two vectors lie on the plane. According to the previous theorem, we know that for any two vectors lie on the same plane, their cross product is always parallel to the normal vector. So let's compute the cross product for u and v first. Let's compute the cross product for vectors u and v first. Write standard base I, j, k in the first row. Write vector u in the second row. And write vector v in the third row. Do the cross product here. Use cofactor expansion. I times the determinant of the matrix -3, 4, -2, 1 minus j times determinant of the matrix -1, 4, 2, 1 plus k times the determinant of the matrix -1, -3, 2, -2. Next, compute the determinant for each matrix individually. I have I times -3 minus -a, which is 5, minus j times -1 minus a is -9, plus k times 2 minus -6, that's a. Then write it in vector form. I have 5, 9, a. Since normal vector is parallel to the cross product of u and v, I can take this as my normal vector. I can take this vector itself as my normal vector. Now we know the normal vector of the plane, and we know a point on the plane. So the equation of the plane can be written as a times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0. This is the normal form of the equation of a plane. In this equation, a, b, c represent the component of the normal vector, and x0, y0, z0 represent a point on the plane. Let's plug in. We have phi 9 a as a normal vector, and x0, y0, z0 is 1, -3, -2. Next, let's simplify. Distribute phi 9 and a. I get phi x minus phi plus 9y plus 27 plus az plus 16 equal to 0. If I combine like terms, negative phi plus 27 is 22. 22 plus 16 is 38. When I bring over, it becomes negative 38. What's left on the left side is phi x plus 9y plus az. This is the standard form of the equation of a plane. That's the standard form of the equation of a plane. If the program doesn't specify how to write the answer, we must always write the answer in the standard form. Next example, find the equation of a plane passing through points 2, 1, 1, 0, 4, 1, and -2, 1, 4. How do we find the equation of a plane passing through 3 points? Consider a plane that contains 3 points. Let's call this 3 point P, Q, and R. If I join PQ, I can find a vector here. If I join PR, I can find another vector on the plane. So here, vector PQ and vector PR, they both lie on the plane. If I join points PQ, I can find a vector lie on the plane. If I join point PR, I can find another vector lie on the plane. Then I can take cross product for PQ and PR. That's the normal vector of the plane. If I take cross product for PQ and PR, if I take cross product for PQ and PR, I find a normal vector of the plane. So let's call this 3 point P, Q, and R. Let's find vector PQ first. For vector PQ, use head minus tail. Q minus P. So 0 minus 2 is -2. 4 minus 1 is 3. 1 minus 1 is 0. Vector PR. Again, head minus tail. Head minus tail. -2 minus 2 is -4. 1 minus 1 is 0. 4 minus 1 is 3. Then we'll take cross product for PQ and PR. PQ cross PR. Put the standard base ijk in the first row. Then write vector PQ in the second row. -2, 3, 0. Write vector PR in the third row. -4, 0, 3. Then take determinant for this matrix. Here we can use cofactor expansion. I times determinant of the matrix 3, 0, 0, 3. J times determinant of the matrix -2, 0, -4, 3. Plus K times determinant of the matrix -2, 3, -4, 0. Then take determinant for each matrix individually. For the first matrix, 9 minus 0 is 9. For the second matrix, -6 minus 0 is -6. For the third matrix, 0 minus -12 is 12. Then if I write this in vector form, I have 9, 6, and 12. For this vector, I can pull out 3, make it a little easier. I can pull out 3. If I pull out 3, I have 3, 2, 4. Since the normal vector is parallel to the cross product of these two vectors, I can take my normal vector to be this vector 3, 2, 4. Then we know a point on the plane. We know a normal vector of the plane. Equation of a plane can be written as a times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0. In this equation, a, b, c represent a component of the normal vector. x0, y0, z0 represent a point on the plane. I can use any point. Let me use point P. I can use any point here. Let me use point P. So plugging a, b, c is 3, 2, and 4. x0 is 2. y0 is 1. z0 is also 1. Then simplify. Write the answer in standard form. We have 3x minus 6 plus 2y minus 2 plus 4z minus 4 equal to 0. Combine like terms. Negative 6 plus negative 2 is negative 8. Negative 8 plus negative 4 is negative 12. When bring over, it becomes positive 12. What's left on the left side is 3x plus 2y plus 4z. That's the standard form of the equation of the plane. Note: in order to find the equation of a plane, we need to find the normal vector of the plane. And a point on the plane. Then substitute into the equation ax minus x0 plus by minus y0 plus cz minus z0 equal to 0. Then simplify. And write the equation of the plane in standard form. Next, let me show you a theorem. Let M be a plane determined by vectors u and v, passing through a point P. Let W and W2 be two vectors lie on plane M. With W and W2, they are not parallel to each other. Then for all vector W, if W also lie on plane M, then W can be written as K1 times W1 plus K2 times W2. For some real numbers, K1, K2. That means W can be written as a linear combination of W1 and W2. Let's prove it. First of all, we know that plane M is determined by vectors u and v. That means for all vectors lie on plane M, we can write a vector as a linear combination of vectors u and v. Since M is a plane determined by vectors u and v, and vectors w1, w2, w lie on plane M. Then I can write each vector as a linear combination of u and v. Then I can write vector w1 as au plus bv, w2 as cu plus dv, w written as can be written as eu plus fv. For some real numbers a, b, c, d, e, f. Next, I try to prove that AD minus BC is not zero. Claim that AD minus BC is not zero. Let's prove it. We'll use this statement to prove that W can be written as K1 times W1 plus K2 times W2. Let me prove this first. So to prove this is not zero, we assume it is zero. Try to prove this by contradiction. We try to show this is impossible. Assume AD minus BC is zero. We try to show this is impossible. Now, assume AD minus BC is zero. In the first equation, I multiply both sides by D. So I have D times W1 equal to ADU plus BDV. Next, I multiply the second equation by negative B. Multiply the second equation by negative B. So I got negative B times W2 equal to negative BCU minus BDV. If I add the equation together, left side is dW1 minus BW2. On the right side, the last term get cancelled. What's left is AD minus BCU. Last term get cancelled. What's left is AD minus BCU. Since AD minus BC is zero, then we have dW1 minus BW2 equal to zero, which means dW1 equal to BW2. Now consider two cases. If both B and D are zero, is it possible? If both B and D are zero, then we have W1 equal to AU, W2 equal to CU. So W1 is parallel to U, to vector U. And W2 is also parallel to vector U. Since W1 is parallel to U, U is parallel to W2, then by transitive property, W1 is parallel to W2. Since W1 is parallel to U, and U is parallel to W2, by transitive property, W1 is parallel to W2. And we know that's impossible because we assume vectors W1, W2, they are not parallel. That's impossible. Then that means B and D, they cannot be both 0. If B and D are not both 0, consider two cases. If B is not 0, if B is not 0 here, I can divide both sides by B. If B is not 0, I can divide both sides by B. Then D over B W1 equal to W2. Here I divide both sides by B. So D over B equal to W2. D over B times W1 equal to W2. Since they are multiple of each other, that means W1 is parallel to W2. That's impossible. Because we assume W1 and W2 they are not parallel. What if D is 0? What if D is 0? In this equation, I divide both sides by D. Then I get W1 equal to B over D times W2. I divide both sides by D. So W1 equal to B over D times W2. Since W1 can be written as a multiple of W2, then they are parallel vectors. That's also impossible. Since all cases are impossible, then we know that since all cases are impossible, therefore AD minus BC cannot be 0. Since all cases are impossible, then we know that AD minus BC cannot be 0. That's all we cut in here. We just prove it. Next, in the first equation here, I multiply both sides by negative C. So I get negative C W1 equal to negative AC times U minus BC times V. I multiply the entire equation by negative C. Next, for the second equation, I multiply the entire equation by A. If I multiply the second equation by A, I have AW1, AW2 equal to ACU plus ADV. If I add these two equations together, we can see that here. The first on the right side can cancel. What's left is AW2 minus CW1 equal to AD minus BCV. Then, in order to get V by itself, I divide both sides by AD minus BC. Since AD minus BC is not 0, I can divide both sides by AD minus BC. Then here, V equal to A over AD minus BC times W2 minus C over AD minus BC times W1. That's vector V. Next, apply the same procedure to get U by itself. In the first equation here, next I'll multiply both sides by D. For the first equation, multiply both sides by D. I have dW1 equal to ADU plus b dv. In the second equation, I multiply both sides by negative b. I get negative b w2 equal to negative bcu minus b dv. If I add them up, on the right side, the last term can cancel. If I add them up on the right side, the last term can cancel. What's left here on the left side is dw1 minus bw2 equal to ad minus bcu. Since ad minus bc is not 0, I can divide both sides by ad minus bc. So I have d over ad minus bc w1 minus b over ad minus bc times w2. Let equal to u. Let equal to vector u. Now next, we try to write vector w as a linear combination of w1, w2. Next, in this equation, I plug in u and v in this equation. So vector w can be written as e times u, e times vector u. Vector u is this vector. It's d over ad minus bc times w1 minus b over ad minus bc times w2 plus f times v. V is this. A over ad minus bc w2 minus c over ad minus bc times w1. Then distribute e and f. It can be rewritten as de over ad minus bc times w1 minus be over ad minus bc times w2 plus af over ad minus bc times w2 minus cf over ad minus bc times w1. Then combine like terms. I have de minus cf over ad minus bc times w1. Combine like terms. They have same denominator, so I can combine numerator together. de minus cf times w1. Then combine these two terms together. They both have w2. They have same denominator, so I can add numerator together. Numerator is af minus be over ad minus bc times w2. So I can take this to be my k1. Take this number to be my k2. Then w equal to k1 times w1 plus w2 times plus k2 times w2. So here w equal to k1 times w1 plus k2 times w2, where k1, k2 are some real numbers here. Next, let's look over this theorem again. This theorem says if w1, w2 are non-parallel vectors on plane M, then for all vector w on plane M, we can always write w as a linear combination of w1 and w2. That means if we know two vectors on a plane, then all vectors on the plane can be written as a linear combination of those two vectors. So keep this in mind. If we know two vectors which lie on a plane, then every vector which lie on a plane can be written as a linear combination of those two vectors. So this theorem says, if we know two vectors which lie on a plane, then every vector which lie on a plane can be written as a linear combination of those two vectors. That's what this theorem says. Keep this idea in mind. Next theorem, let W1 and W2 be non-parallel vectors which lie on plane M. If vector M is perpendicular to W1 and W2, then M is the normal vector of plane M. Let's prove it. For this problem, in order to show n is a normal vector of plane M, we try to show that n is perpendicular to all vectors which lie on plane M. We try to show n is perpendicular to all vectors which lie on plane M. So let W be a vector which lie on plane M. Since W1 and W2 are two non-parallel vectors, which lie on plane M, then by the previous theorem, if there are two non-parallel vectors lie on plane M, every vector on plane M can be written as a linear combination of vector W1 and W2. Then by the previous theorem, vector W can be written as linear combination of W1 and W2. That means K1 times W1 plus K2 times W2, where K1, K2 are real numbers. For some real numbers, K1, K2. Since W1 and W2 are non-parallel vectors on plane M, then for all vector W on plane M, I can write W as a linear combination of W1 and W2 by the previous theorem. Here, since vector N is perpendicular to both W1 and W2, then their dot product must be 0. Next, I take dot product for W and N. N dot W. I replace W with K1 W1 plus K2 W2. Distribute N. I get N dot K1 W1 plus N dot K2 W2. Here I can pull out K1, K2. So this can be rewritten as K1 times N dot W1 plus K2 times N dot W2. Since the dot product of N1 W1 is 0, N2 W2 is also 0, then The whole expression here is 0. Since n dot w is 0, since their dot product is 0, means n and w are perpendicular. This vector n and vector w are perpendicular. So n is perpendicular to vector w. And here, vector w is an arbitrary vector which lies on plane M. That means vector n is perpendicular to every vector which lies on plane M. Since this is an arbitrary vector. Since n, if n is perpendicular to w, that means n is perpendicular to every vector which lies on plane M. So n is perpendicular to every vector which lies on plane M. Since n is perpendicular to every vector which lies on plane M, M must be a normal vector. Since n is perpendicular to every vector which lies on plane M, M must be the normal vector of plane M. So this theorem says, if n is perpendicular to two non-parallel vectors on a plane, then M must be the normal vector of the plane. This theorem says, if a vector n is perpendicular to any two non-parallel vectors on a plane, then this vector n must be the normal vector of the plane. So keep this in mind. Note, if a vector is perpendicular to any two non-parallel vectors which lie on a plane, then this vector must be the normal vector of the plane. If a vector is perpendicular to any two non-parallel vectors which lie on a plane, then this vector must be the normal vector of the plane. That's what this theorem says. Keep it in mind. Next example, let x minus 2y plus z equals 0 and 2x plus 3y minus 2z equals 0 be equations of two planes. Part A, find the angle between the planes. Part B, find the intersection of the planes. So here we have two planes. We try to find the angle between the planes and the intersection of the planes. Let me first of all draw the picture first. We have two planes here. Let me call the first plane M1, call the second plane M2. In part A, we're looking for the angle between the planes. That means we're looking for this angle here. Let's call this angle theta. In order to find angle theta, let me first of all change my eye level. If I change my eye level, I can make two planes, looks like two lines. if I change my eye level, I can make my plane 1, plane 2 looks like two lines, two straight lines. By changing my eye level, I can make two planes looks like two lines. This is plane M1, this is plane M2. Angle theta is here. If I change my eye level, I can make these two planes looks like two lines. And the angle, there's an angle between these two planes. Next, let me draw the normal vector for both planes. Let me first of all draw the normal vector for plane M1. Yes, let me call this angle, and let me call this vector N1. Normal vector is perpendicular to the plane. Next, I'll draw normal vector for plane M2. Start from intersection here. Normal vector is the vector that perpendicular to the plane. So that's a right angle. Let me call this angle N2. Let me call this vector N2. So here, N1 is the normal vector of plane M1. N2 is the normal vector of the plane M2. Let me label this angle here. Let me call this angle alpha, beta, gamma, and delta. Let me call this angle alpha, beta, gamma, delta. We know that this is a triangle. The inscribed angle of a triangle must be 180 degrees. So angle theta plus alpha plus gamma must be 180 degrees. And we know that angle gamma is a right angle. Gamma is a right angle. It must be 90 degrees. If I substitute 90, theta plus alpha plus 90 equal to 180. So theta plus alpha must be 90 degrees. Next, we know that this angle here is a right angle. So angle alpha plus beta must be 90 degrees. This is a right angle. So angle alpha plus beta must be 90 degrees. If I combine these two equations together, they both equal to 90 degrees. I can write angle theta plus alpha equal to alpha plus beta. For these two equations, they both equal to 90 degrees. So theta plus alpha equal to alpha plus beta. Subtract alpha from both sides. Subtract alpha from both sides. Angle theta is the same as angle beta. Next, since angle beta and angle delta, they are vertical angles. Angle beta and angle delta, they are vertical angles, so they must be the same. Since angle beta and angle delta, they are vertical angles, then they must be the same. Beta must be the same as delta. Since theta is the same as beta, beta is the same as delta, so theta must be the same as delta. Theta must be the same as delta. Since theta is the same as beta, and beta is the same as delta, then angle theta must be the same as angle delta. So here we can see that the angle between these two planes is the same as the angle between their normal vectors. Here we can see that the angle between these two planes is the same as the angle between their normal vectors. So keep this note in mind. The angle between two planes is the same as the angle between their normal vectors. is the same as the angle between their normal vectors. Now you can find the angle between the planes. First of all, let's find their normal vectors. n1 equal to 1, -2, and 1. The component of the normal vector is always the same as the coefficient of s, y, z. And similarly, n2 equal to 2, 3, -2. The component of the normal vector is the same as the coefficient of s, y, z. And we know that the angle between the planes is the same as the angle between their normal vectors. So let's find the angle between these two normal vectors. Here we use the formula cosine theta equal to the dot product of n1 dot n2 over the magnitude of n1 times magnitude of n2. Let's first of all compute the dot product between n1 and n2. n1 dot n2 equal to 1 times 2 is 2, -2 times 3 is -6, 1 times -2 is -2, 2 minus 6 minus 2 is -6. Next, we compute the magnitude of n1. Use Pythagorean theorems. We have square root of 1 square plus -2 square plus 1 square. That's 1 plus 4 plus 1. That's square root of 6. Magnitude of n2. Again, we use Pythagorean theorem. That's square root of 2 square plus 3 square plus -2 square, which is 4 plus 9 plus 4. 13 plus 4 is 17. I get square root of 17. Then plug in, we can find cosine theta, where theta is the angle between the planes, between the vectors. Here, cosine theta is -6 over square root of 6 times square root of 17. That's square root of 6 over square root of, if I multiply 6 times 17, I get 102. Then, this is cosine theta. For theta itself, I can apply inverse cosine. Inverse cosine of -6 over radical 102. Here I use my calculator. I get 53.55 degrees. That's the angle between these two normal vectors, which is the same as the angle between the planes. That's the angle between these two planes. Here, according to this problem, we know that the angle between two planes is always the same as the angle between their normal vectors. So we can say that if the normal vector of two planes are parallel, then two planes are parallel to each other. And if the normal vector of two planes are perpendicular, then two planes are perpendicular to each other. So keep this note in mind. Let M1 and M2 be two planes. We say M1 is parallel to M2 if their normal vectors are parallel. We say M1 is perpendicular to M2 if their normal vectors are perpendicular. Let me show you the picture here. It will make more sense to you. assume that's M1, that's M2. That's the normal vector of M1 called N1. That's the normal vector of M2 called N2. We can see that if the normal vector of these two planes are parallel, then these two planes, M1, M2, are parallel to each other. Next, let me show another picture for perpendicular planes. Assume that's M1. M2 is a perpendicular plane. Assume that's M2. Let me draw the normal vector for both planes. Let N1 be the normal vector of M1. And let N2 be the normal vector of M2. Assume that's N2. So you can see that if N1 and N2 are perpendicular, then these two planes must be perpendicular. If N1 and N2 are perpendicular, then these two planes must be perpendicular. So when the normal vectors are parallel, two planes are parallel. When the normal vectors are perpendicular, two planes are perpendicular. Part B, find the intersection of the planes. Those are the two planes, M1 and M2. Here we can see that the intersection of these two planes is a straight line here. If we want to find the equation of this straight line, we must know 2 points on the line. How do we find 2 points on the line? Let's call it 2 points P and Q. Since this line lies on the intersection of these two planes, then all points on the line must satisfy the equation of both planes. So that means point P and Q must satisfy the equation of both planes. In order to find points P and Q, I try to combine both equations together by eliminating one of the variables. If I multiply first equation by 2, I get 2x minus 4y plus 2z equal to 0. And I leave the second equation the same. I get 2x plus 3y minus 2z equal to 0. When I add the equation together, we can see that z get cancelled. So I have 4x minus y equal to 0. So for point P, I let s equal to 0. If I let s equal to 0, solve for y, I get 4 times 0 minus y, which means y is also 0. If I plug in s and y into one of the equations, I can find z. Here I plug in s and y into the first equation, I get 0 minus 2 times 0 plus z equal to 0. Solve the equation for z is also 0. So point P is the point 0, 0, 0. Then for point Q, I pick different value. We can pick value for x or y, whichever is easier. Let me pick value for x. If I let s equal to 1, I have 4 times 1 minus y equal to 0. Solve the equation for y equal to 4. Then I can plug in s and y into the first equation and solve for z. We can plug into either equation, make it easier. Let me use the first equation. 1 minus 2 times 4 plus z equal to 0. That means negative 7 plus z equal to 0. So z equal to 7. So point Q is the point 1, 4, 7. Once I know 2 points on the line, if I join the points, I can find the directional vector of the line. So the directional vector is the same as vector PQ. For vector PQ, I use head minus tail, Q minus P. 1 minus 0 is 1. 4 minus 0 is 4. 7 minus 0 is 7. That's the directional vector. And for position vector R0, I can use either P or Q, whichever is easier. Here, P is easier. So I can use 0, 0, 0 as a position vector. Equation for line is R of t equal to R0 plus TV. Plug in. R0 is the point 0, 0, 0. T times V. V is the vector 1, 4, 7. Then distribute 7. Distribute T. We have 0, 0, 0 plus T, 4T, 7T. Then add the vectors. We get T, 4T, 7T. If we want to answer as a parametric equations, we have S equal to T, Y equal to 4T, Z equal to 7T, where T can be any real number. These parametric equations represent the equation of this line. This parametric equation represents the equation of this line, which is the intersection of these two planes. Next, let me show you some distance formulas. How do we find distance between 2 points? Let P and Q be 2 points in R3. Find the distance between P and Q. When we have 2 points, P and Q, if I join 2 points, I can find a vector PQ. The distance from P to Q is the same as the magnitude of this vector PQ. Distance from P to Q is the same as the magnitude of the vector PQ. So that's a simple formula. Next, how do we find the distance from a point to a line? Let L be a line, and let Q be a point with Q doesn't belong to L. That means point Q doesn't lie on line L. Find the distance from point Q to line L. So L is a line. Q is a point that doesn't lie on line L. Suppose Q is here. We are looking for distance from point Q to line L. Distance from point Q to line L. Let's draw a perpendicular line from point Q to line L. This is the distance from point Q to line L. How do we find distance from point Q to line L? Let me first of all pick point P on line L. Pick point P on line L. Then connect point PQ, I can make vector. If I join PQ, I can find a vector here. This is vector PQ. Let V be the directional vector of line L. let V be the directional vector of line L. And let's set up an angle between these two vectors. Let's set up an angle between vector V and vector PQ. Now here we have a right triangle. Here we have a right triangle. D is an opposite side, and PQ is an hypotenuse. D is an opposite, PQ is hypotenuse. In a right triangle, if we know the opposite and hypotenuse, we can use sine function. So we know that sine theta is opposite over hypotenuse, which is D over magnitude of vector PQ. So sine theta equal to D over magnitude of vector PQ. If I solve this equation for D can be written as magnitude of vector PQ times sine theta. Here, since angle theta varies from 0 to 180 degrees, and sine function from 0 to 180 is always positive. Sine function from 0 to 180 is always positive. So this formula guarantees D is always positive. Since sine theta from 0 to 180 is always positive. So this formula guarantees D is a positive number. Next, how do we find sine theta? How do we find expression for sine theta? Theta is the angle between these two vectors, vector V and vector PQ. So sine theta can be written as the magnitude of the cross product PQ cross V over magnitude of PQ times magnitude of vector V. If I plug in sine theta here, D can be written as magnitude of PQ times magnitude of PQ cross V over magnitude of PQ times magnitude of V. Then here I can cancel PQ from top and the bottom. I have magnitude of PQ cross V over magnitude of V. So that's the distance from point Q to line L. So here distance formula is magnitude of PQ cross V over magnitude of V. In this formula, Q is the given point. Point Q is the given point. Point P could be any point light on line L. So P is a point on line L. V is the directional vector of line L. Here V is the directional vector . So Q is a given point. P is a point on line L. V is the directional vector of line L. That's the distance formula for distance from a point Q to line L. That's the distance formula for distance from a point Q to line L. Next, how do we find the distance between two parallel lines? Let L1 and L2 be two parallel lines. Find the distance between L1 and L2. Let me show you the picture first. We have two parallel lines, L1 and L2. Let me call this line L1, call this line L2. We try to find the distance between these two lines. How do we find the distance here? Let me first of all pick point Q on line 2. Let Q be a point on line 2. Then here we can see that the distance between these two lines is the same as the distance from point Q to line 1. The distance between these two lines is the same as the distance from point Q to line 1. Since we are looking for the distance from a point to a line, we can use the previous formula, distance from point to a line. So we can use the same formula here. D equal to magnitude of point PQ cross vector V over magnitude of vector V. Now, what does PQ and V means in this formula? Let's try to match in the previous picture. P is a point on this line here. So in this problem, P must be a point on line 1. In this formula, P is a point on line 1. And we can see that here, Q is a point on line 2. How about V? In this picture, V is a vector on line L. So here, V must be a vector on line 1. Here, V must be a vector on line 1. V must be the directional vector of line 1. But line 1, line 2, they are parallel. So V could be the directional vector of either line 1 or line 2. Since line 1 and line 2, they are parallel. V could be the directional vector of either line 1 or line 2. Here, V could be the directional vector of either line 1 or line 2. The picture is the same. That's vector PQ. Let's angle theta between these two vectors. So that's the distance formula for distance between two parallel lines. That's the distance formula for distance between two parallel lines. In this formula, P is a point on line 1, Q is a point on line 2. V is the directional vector of either line 1 or line 2. Next, how do we find the distance from a point to a plane? Let M be a plane, and the Q be a point with Q doesn't belong to M. That means point Q doesn't lie on plane M. Find the distance from point Q to plane M. How do we find distance from point Q to plane M? Let's draw the picture first. Suppose that's plane M. Q is a point that doesn't belong to plane M. We try to find distance from point Q to plane M. How do we find distance here? Let's first of all pick point P on plane M. Let P be a point on plane M. Then join point P and Q, I can find a vector PQ. Join P and Q, I can find vector PQ. Next, I can draw a normal vector of plane M at point P. That's normal vector N. And that's an angle between these two vectors. Let's call this angle theta. Next, let's draw a perpendicular line from point Q to plane M. Let's draw a perpendicular line from point Q to plane M. Assume the intersection here is point O. Let's draw a perpendicular line from point Q to plane M. And the intersection here is point O. Then the distance from O to Q is the distance from point Q to plane M. This is distance from point Q to plane M. Then connect point OP. Connect point OP. This must be a right angle here. This must be a right angle here because this line OQ is perpendicular to plane M, and OP is a line light on plane M. So these two lines must be perpendicular. Next, I can draw a perpendicular line from point Q to vector n. Draw a perpendicular line from point Q to vector n. Draw a perpendicular line from point Q to vector n. Then here we can see that these two lines are parallel line because this line perpendicular to plane M. Normal vector n is also perpendicular to plane M. So these two lines are perpendicular lines. Since this line is perpendicular to vector n, this line is also perpendicular to vector n. So this must also be perpendicular lines, must also be parallel lines. Since the opposite lines are parallel, and there are right angles here, this must be a rectangle. This must be a rectangle. In the rectangle, the opposite side must be the same. So this side must also be D. This side must be the same. This side is also D. Now, in this right triangle, D is the adjacent side. Vector PQ is the hypotenuse in this right triangle here. D is the adjacent side. Vector PQ is the hypotenuse. If we know the adjacent and hypotenuse, we can use cosine function. So cosine theta is adjacent over hypotenuse. D over magnitude of vector PQ. If we solve this equation for D can be written as magnitude of vector PQ times cosine theta. Here, angle theta varies from 0 to 180. For angle between two vectors, angle theta varies from 0 to 180. For cosine function from 0 to 180, it may be positive, may be negative. There's no guarantee it's always positive. But D is always positive. So in order to make D positive, we must take absolute value for cosine theta. So for theta from 0 to 180, cosine theta varies from -1 to 1. There's no guarantee D is always positive. But D is a distance, it must always be positive. So in order to make D positive, we must take absolute value for cosine function. Since D is always positive, distance formula is distance is always positive. Since D is always positive, so we must take absolute value for cosine. Next, how do we find cosine? How do we find expression for cosine? We know that angle theta here is an angle between vector PQ and vector n. Theta is angle between vector PQ and vector n. So for cosine theta, there's a formula that says cosine theta equal to the dot product of PQ dot n over the magnitude of PQ times magnitude of n. If I plug in cosine here, I have magnitude of PQ times absolute value of PQ dot n over magnitude of PQ times magnitude of n. Since the denominator is the magnitude, it's always positive. So we only apply absolute value to the numerator. The denominator is always positive. So we only apply absolute value to the numerator. Then here I can cancel PQ. If I cancel PQ, what's left is absolute value of PQ dot n over magnitude of vector n. So the distance formula can be written as d equal to absolute value of pq dot n over magnitude of n. That's the distance for distance from a point to a plane. Here, q is in this formula, q is a given point. Q is a given point. P could be any point on plane M. P is a point on plane M. It could be any point on plane M. N. Here, n is a normal vector of plane M. N is a normal vector of plane M. N is a normal vector of plane M. So that's the distance formula for distance from a point to a plane. That's the distance formula for distance from a point to a plane. Next, how do we find the distance between two parallel planes? Let M1 and M2 be two parallel planes. Find the distance between M1 and M2. How do we find the distance between M1 and M2? Let's draw the picture first. Assume these two planes are M1 and M2. They are parallel to each other. How do we find distance between M1 and M2? Let's first of all pick point Q on M2. Then draw a perpendicular line from point Q to M1. Now you can see that the distance between M1 and M2 is the same as the distance from point Q to M1. The distance between these two planes is the same as the distance from point Q to M1. Then, for the distance from a point to a plane, we can use the previous formula. For the distance from a point to a plane, we can use the previous formula. D equal to the absolute value of dot product PQ dot N over the magnitude of N. Then in this formula, what does PQ and N means? Let's try to match the picture here. Let's match the previous picture. P is a point on plane M. So here, P must be a point on plane 1. Here, P is a point on plane 1. On plane M1. Q is a point on plane M2. Here, Q is a point on plane M2. How about N? Here, N is a normal vector of plane M. So M must be the normal vector of plane M1. This is vector n. M must be the normal vector on plane M1. But since plane M1 and M2 they are parallel planes, their normal vector must be parallel. So n can also be the normal vector of plane M2. Since M1 and M2 they are parallel planes, their normal vector must also be parallel. So n could be the normal vector of either M1 or M2. N could be the normal vector of either plane M1 or plane M2. That's the distance formula for distance between two parallel planes. That's the distance formula for distance between two parallel planes. Next, how do we find the distance between two skew lines? Let L1 and L2 be two skew lines. Find the distance between L1 and L2. Here, L1 and L2 they are two skew lines. That means they are not parallel and they are not intersecting each other. How do we find their distance? Keep this idea in mind. For any two skew lines, we can always find two parallel planes, where each plane contains one of each line. Let me show you the picture first. Here, L1, L2 are two skew lines. Let me call this line L1. Call this line L2. Then, for any two skew line, we can always find two parallel planes, where each plane contains one of each line. Let me call this plane M1. Call this plane M2. Here, plane M1 contains line 1. Plane M2 contains line 2. We try to find the distance between line 1 and line 2. Here we can see that the distance between line 1 and line 2 is the same as the distance between plane M1 and plane M2. The distance between these two lines is the same as the distance between these two planes. For distance between two planes, we can use the old formula here. The previous formula says the distance between two planes is the absolute value of PQ dot n over magnitude of n. So we can use the same formula to find distance between these two planes. So distance between two planes is absolute value of vector PQ dot n over the magnitude of vector n. Now, what does PQ and n means here? What does PQ and n means? Let's look at the previous picture here. P, here in the previous picture, P is a point on plane M1. So here we can pick point P on line 1. Since line 1 lies on plane 1, since line 1 lies on plane M1, point P also lies on plane M1. So P is a point on line 1. How about Q? In the previous formula, Q is a point on plane M2. So here we can pick Q on line 2. We can pick point Q on line 2. Since line 2 lies on plane M2, point Q also lies on plane M2. So let Q be a point on line 2. Now, how about vector n? How about vector n? In the previous formula, n is the normal vector of plane M1 and M2. In the previous problem, n is the normal vector of plane M1 and M2. Here, how do we find a normal vector for plane M1 and M2? How do we find the normal vectors? Consider these two lines, L1 and L2. They are not parallel lines. They are not parallel. That means their directional vectors are not parallel to each other. If I find a cross product, I can find a vector that's perpendicular to both lines. The directional vector of line 1 is called v1. Let v1 be the directional vector of line 1. And let v2 be the directional vector of line 2. If I take cross product, I can find a vector that's perpendicular to both vectors. So this vector will be perpendicular to both planes, M1 and M2. Since this vector is perpendicular to both lines, L1 and L2, it must be perpendicular to both planes, M1 and M2. So I can take this vector n to be the normal vector of both planes. I can take this vector n to be the normal vector of both planes. Then I can shift this vector to point P. Shift this vector to point P. If I shift this vector here, this is the same vector n. This is the same normal vector. Connect PQ. That's vector PQ. Connect these 2 points. This is a right angle. Because this is normal vector. Normal vector is perpendicular to plane M2. So this must be a right angle here. That's angle theta. From this point to this point is the distance from plane M1 to plane M2. From this point to this point, that's the distance between plane M1 and plane M2, which is also the distance from line 1 to line 2. It's D. That's angle theta. This is a right triangle. So here, n is the normal vector of these 2 planes. So n can be written as the cross product of v1 cross v2. Or to make it easier, n can be any vector parallel to the cross product of v1 cross v2. Where v1 and v2 are the directional vector where v1 and v2 are the directional vectors of line 1 and line 2. So that's the formula for distance between 2 skew lines. That's the formulas for distance between 2 skew lines. That's the formulas for distance between 2 skew lines. Next, let's look at an example. Let 3, -1, 4 be a point, and let s equal to -2 plus 3t, y equal to -2t, g equal to 1 plus 4t represent equations of a line. Find the distance from the point to the line. So for distance from a point to a line, we can use the formula d equal to magnitude of vector pq cross v over magnitude of vector v, where p is a point on the line, q is the given point, v is the directional vector of the line, p is a point on the line, q is the given point, v is the directional vector of the line. So here, for point P, let t equal to 0, If I plug in 0 for t, then I have s equal to -2, y equal to 0, g equal to 1. So point P is the point -2, 0, and 1. Q is the given point. Q is the given point. 3, -1, 4. Vector V is the directional vector. Directional vector of a line is the coefficient of t. Directional vector of a line is the coefficient of t. Coefficient of t here is 3, -2, and 4. That's vector V. Then plug into the formula. We first of all find vector PQ first, then find a cross product between PQ and V. So for vector PQ, use Q minus P, head minus tail. For vector PQ, use Q minus P. 3 minus -2 is 5. -1 minus 0 is -1. 4 minus 1 is 3. That's vector PQ. Then we find a cross product. PQ cross V. Find a cross product. PQ cross V. Let's write ijk in the first row. Put vector PQ in the second row. Write vector V in the third row. Then compute the determinant. Use cofactor expansion. I get vector I times determinant of the matrix -3, -1, 3, -2, 4 minus vector J times determinant of the matrix 5, 3, 3, 4 plus vector K times determinant of the matrix 5, -1, 3, -2. Then compute each determinant individually. I get I times determinant of this matrix -4 minus -6, which is 2, minus J times magnitude of this matrix, which is 20 minus 9, that's 11, plus K times determinant of this matrix, that's -10 minus -3, which is -7. Write it in vector form. That's the vector 2, -11, and -7. Then we must compute the magnitude of the cross product. Magnitude of PQ cross V is square root of 2 square plus -11 square plus -7 square. That's 4 plus 121 is 125. 125 plus 49, that's 174. That's the numerator. Then for the denominator, we compute the magnitude of vector V. This is vector V here. Take the magnitude. I get square root of 3 square plus -2 square plus 4 square. 3 square is 9. -2 square is 4. 9 plus 4 is 13. 4 square is 16. 13 plus 16 is 29. Then use the formula. D equal to the magnitude of PQ cross V over magnitude of V, which is square root of 174 over square root of 29. 174 divided by 29 is 6. So I get square root of 6. That's the distance between this point and this line. It's the distance from a point to a line. Next example, find the distance from the point 1, 5, -4 to the plane 3x minus y plus 2z equal to 6. So for distance from a point to a plane, we use the formula D equal to the absolute value of pq dot n over the magnitude of vector n, where p is a point on the plane, q is the given point, n is the normal vector of the plane. So for point P, we need to find a point on this plane. So plug in some value for x and y, and solve for z, you can find a point. Let s equal 0, y equal to 0. Then we have 2z equal to 6. So z equal to 3. So P is a point 0, 0, 3. Q is the given point. Q is the given point. So point Q is the point 1, 5, -4. That's a point. Once I know 2 points, I can find the vector. I can find vector PQ. For vector PQ, use head minus tail, Q minus P. So I get 1, 5, -4 minus 3 is -7. That's vector PQ. Then for vector V, for vector N, N is a normal vector of the plane. N is a normal vector of the plane, which is 3, -1, 2. Then we compute the dot product. On the numerator, compute the dot product. PQ dot N is 1 times 3 is 3. 5 times -1 is -5. -7 times 2 is -14. Adding up, 3 minus 4 is -2. -2 minus 14 is -16. And in the numerator, we must take absolute value from the dot product. So take absolute value. Absolute value of PQ dot N must be absolute value of -16. So it must be positive 16. That's the numerator. Then from the denominator, we compute the magnitude of vector N. Magnitude of vector N is square root of 3 square plus -1 square plus 2 square. 3 square is 9. 1 square is 1. 9 plus 1 is 10. 10 plus 4 is 14. That's square root of 14. Then plug into the distance formula. So the distance between the point and the plane, distance from the point to the plane is 16 over square root of 14. That's the distance from this point to this plane. Next example, let two skew lines L1 and L2 be defined as L1 x equal to 2 plus 2t, y equal to 4 minus 2t, z equal to 4t. L2 s equal to 4 minus 3t, y equal to 4 plus 4t, z equal to 1 minus 2t. For the distance between the lines. So for the distance between two skew lines, we use the formula d equal to the absolute value of PQ dot N over magnitude of vector N. So here, in this formula, P is a point on line 1, Q is a point on line 2, and N is the cross product of V1 and V2. V1 and V2 are the directional vector of line 1 and line 2. So for point P, P is a point in line 1. In line L1, let t equal to 0. If I let t equal to 0, I have s equal to 2. Y equal to 4 and z equal to 0. So P is the point 2, 4, 0. Q is a point in line 2. So for point Q, in line L2, let t equal to 0. If I plug in 0 to line 2, I have s equal to 4, y equal to 4, z equal to 1. So Q is a point 4, 4, 1. So that's vector PQ. So for vector PQ, I use head minus tail. Head minus tail, Q minus P. 4 minus 2 is 2. 4 minus 4 is 0. 1 minus 0 is 1. That's vector PQ. Next, for vector n, we must find the directional vector for both lines, for line 1 and line 2 first. V1 is the directional vector of line 1, which is the coefficient of t's in line 1, which is 2, -2, and 4. The coefficient of t are the directional vector of line 1. That's 2, -2, and 4. Coefficient of t, 2, -2, and 4. V2 is the directional vector of line 2, which is the coefficient of t in line 2. We have -3, 4, and -2. Next, for vector n, I find a cross product for V1 and V2. Write I, J, and K in the first row. Write vector V in the second row. Write V2 in the third row. Then find the determinant. Use covector expansion. I get I times the determinant of the matrix -2, 4, 4, -2, minus J times determinant of the matrix 2, 4, -3, -2, plus K times determinant of the matrix 2, -2, -3, and 4. Then compute each determinant individually. I get I times 4 minus 16 is -12, minus J times -4 minus -12, that's positive A, plus K times A minus 6. A minus 6 is 2. Then write in vector form, I have -12, -A, and 2. For this vector, I can factor. I can pull out -2, make it a little easier. I can pull out -2. I get 6, 4, and -1. I can take this as my normal vector, as vector n. N could be any vector that parallel to the cross product of V1 and V2. To make it easier, take this vector to be vector n. So n equal to 6, 4, -1. Let me copy everything here, then continue the computation. Next, I find the dot product PQ dot n, which is 2 times 6 is 12. 0 times 4 is 0. 1 times -1 is -1. 12 minus -1 is 11. Then when I take absolute value for PQ dot n, I get positive 11. Next, I find the magnitude of vector n. That's square root of 6 squared plus 4 squared plus -1 squared. 6 squared is 36. 4 squared is 16. 36 plus 16 is 52. 1 squared is 1. 52 plus 1 is 53. So the distance between two skew lines is 11 over square root of 53. That's an answer.